But without further ado, I want to move on to Dr. Bryce Richardson. Bryce is going to present on the Climate Smart Restoration Tool. Bryce is a plant research geneticist with the U.S. Forest Service's Rocky Mountain Research Station. His focus is on understanding plant population, evolutionary relationships, adaptive genetic variation, and their application to restoration. So thanks for joining us today, Bryce.
Thanks, Sean. So I thought I'd start by just describing some seed transfer tool concepts, and then we'll talk about the Climate Smart Restoration Tool and some ongoing updates to that as well. So a little history and need for seed transfer. As many of you know, population genetic adaptation is ubiquitous in all organisms. In plants, adaptation is primarily through climate, although there's others. And most commercial tree species are now managed through seed transfer zones based on adaptive traits. Climate change, however, will upend reliance on static seed transfer zones. So we need to develop more dynamic seed transfer approaches to evaluate these changes and use them for assisted migration. So one concept I wanted to cover were the two different types of seed transfer. One of them is called zonal, and that's where you take your variation, your climate variation or your trait function variation, and parse it up into regular segments, and you get something like you see down on the left, these generalized seed transfer zones by Bauer and et al. The other way to do this is called a focal point seed transfer approach, and that's where it draws the limits out from a specific point. As you can see on the right here, I have a point near one of our experimental forests in northern Idaho. So some pros and cons to both of these approaches. Zonal is easy to implement. They're static, so you can make maps. However, they're less accurate, especially near the margins of these zones. And they become increasingly complex, and some of these zones even become ephemeral with climate change. For focal point zones, they're much more accurate, and they're dynamic, so they can accommodate these climate change projections. However, they're difficult to implement. That's where a web tool comes into effect, that we can generate these things on the fly. So the other concept is this generalized versus empirical seed transfer approaches. So a generalized approach uses solely environmental variables to estimate seed transfer. And in most cases, this is this climate variation. Whereas a empirical seed transfer approach is using the relationship between traits and the environment, usually climate, to describe the variation in those traits. And these, of course, are species specific. Some examples of the variation you get from doing these common gardens and empirical seed transfer is this excellent example on the left here, showing the variation in growth in Sitka spruce, where you get high growth rates in warmer climates and much slower growth rates in colder climates. You can also display this graphically on the right here, where you have, this is big sagebrush, where you have the flowering date, the Julian date for sagebrush on one axis, and the other axis is the accumulation of degree days reaching 100, which is a way of describing springtime. So for a fall flowering plant, plants that have early springs flower later in the year, is what this relationship is telling you, and vice versa. So what I thought I'd do is kind of go through the Climate Smart Restoration tool. Here's the website for it. And this publication describes kind of the methods we've used for it. So let me switch gears here a little bit. Okay, you all see that? So what I thought I'd do is kind of run through the steps that you would use to develop some seed zone guidelines for your site. And like Michelle and Catherine, I'll focus in on this southern part of the Craters of the Moon site. The first step in this is selecting the objective. And you see two options here: find seed lots. So that's finding seed for your particular site. Or the other option is find planting sites. So that's if you collected seed from the site and we're going to use it elsewhere. And these are the same as long as you keep both the current and the future the same. So if you have these both selected for the same time period, they're going to be the same. But if you change when should these plants be best adapted to the planting site, this will change the outcomes. Just a heads up. So you go through these steps. You add your site location. Third step is kind of does it on the fly. It just helps speed things up. And then you select your climate scenarios. So you have two historics. You have kind of older one that's good for longer lived species, and then a more contemporary one from 1981 to 2010. And then you have where you want your future climate to be. So if you want it to stay the same, or if you want, mid-century, you have two options here for different scenarios. That Catherine was describing, either RCP 4.5 or 8.5. We'll do that. And then this fifth step, this is where you choose between empirical seed zone or a generalized seed zone. So custom is your generalized seed zone, and you'd select your variables that you want to use here. Or if you wanted to use empirical seed zone, which we have a few up right now. So for Wyoming Basin Big Sagebrush, it already selects the traits that are used to create those. And then in step 6, so it's already auto-populated for you, and it is for the rest of these species. And then you can apply constraints to this projection too. So for these empirical seed zones, I would recommend just using the species range. This is the species distribution model for that particular species. So you select Wyoming Big Sagebrush, and then you can run the tool. So let me jump back to PowerPoint. And I'll kind of show you the output from these tools. So this is the same point I was showing you on the example on the website. This is empirical seed zones for Wyoming Big Sagebrush. The colors you see on there from yellow to red is the gradient shows climate similarity. So yellow being low similarity, red being higher, but they're all within the projected seed transfer zone for this particular site. So you can see current, you can see this is where things match up for the site. And if we move into mid-century, this is for RCP 8.5. Again, we see things move south for where you want to collect your seed, especially into Utah. If we move to blue bunch wheatgrass empirical seed zones, this is a different model, so you're expecting different results. But you can see that by mid-century, under the same scenario, you see local seed sources are no longer adapted to this site. We'll have to look elsewhere. One of the issues with quantitative seed transfer is they're only available for a handful of species, especially in rangelands. And they require 3 to 6 years to develop. So we're really looking at a scenario where we're going to be short on time to develop these and have the information to conserve the genetic resources that exist out there before things start to fall apart and we start to lose some of our adaptive variation. This is where generalized seed transfer techniques, I think, come in because they provide immediate results and kind of can act as a stopgap to start restoration programs for these species that lack this genetic information. So again, pros and cons of generalized seed transfer. The pros is they can be used for all plants, and they use, in this case, Euclidean distance to measure these differences in climate. Our current seed transfer tool, Climate Smart Restoration tool, uses an approach where you select the climate variables that you'd like to use, and we recommend these 2 variables that I have up here: mean coldest month temperature, and then the transfer limit of plus or minus 2 degrees C, and summer heat moisture index times a half, and that gives you a pretty good idea of estimate of seed transfer. However, it's still a bit of a sandbox, and a lot of your users have trouble determining what climate variables are best. So it has issues, I'll just put it that way, for some people. And oftentimes a 2 variable model kind of over projects the actual seed transfer that we've seen. So we've been working on developing a new climate analog method, and this method uses the same focal point seed transfer approach, but it uses 19 climate variables to calculate this, and these are all standardized. And then we have 3 different thresholds to accommodate both risk that you'd be willing to take and whether the species is more narrowly or broadly adapted. So for a broadly adapted species, you might want to use more of a weak threshold versus a more narrowly adapted species. I would recommend a strong threshold here. And then the interesting thing about this new tool is that it uses a nearest neighbor algorithm to find climate analog sites in vegetative databases. So we have approaching 700,000 vegetative plots that we can use to drill down to see what these sites are made of, what the species composition is like. And here's this table showing the data that's available. Not all these have species information, but all the bottom 4 listed there do. So we have the FIA data set from the Forest Service, and then we have the BLM AIM data set as well. So on average, there's about 1 plot every 12 kilometers across North America. And I should mention, we also have Mexico and Canadian inventory data as well, at least for forest species. So this is an example of this new climate analog output. And this is in the Puget Sound area of Washington. So the yellow diamond shows the reference point or the focal point that we're looking at. And the green polygon shows you the total area under the weak threshold. And then the points are actual plot data, where red equals a strong threshold, violet equals kind of a moderate, and blue the weak. And then we also added some white points that are outside the threshold, but kind of along the margins. So you can see in figure A here, this is the contemporary climate for this site. And then in the future, you can see how drastic the reduction in analogs are by mid-century, where we only have a few analogs that light up down in the Columbia Gorge. So we can also do this for our Craters of the Moon site. And you can see currently we have quite a few analogs, both locally and in other in similar climates in Northwest Nevada and Utah. And then by mid-century, you can see a similar pattern here that I showed with some of these other outputs, where you see things shift to the south and to Utah mainly, where we get these analogs. And then if we start to kind of look at this compiled species that are from these different vegetative plots, you can get a good idea of how these areas, these sites may change in the future. So this is all for mid-century. That's the future plot, and the contemporary current plot is shown there in those two columns. What I did was just selected the top 5 forbs, shrubs, and grasses in this list, and you can see that all these natives decline to some degree at this Craters site. And some more bad news: weeds across the board increase. So we got our work cut out for us, I think, for some of these sites. I think it's better as you move up in elevation and worse as you move down, which the literature supports here as well. And this is another figure that we've shown in a recent publication where this got us curious. So what we did was we looked at 60 sites in the sagebrush biome and found a relationship between how many analogs are available and summer dryness index, which is kind of the relationship between the accumulation of growing degree days through the summer and total moisture during the summer. So the break point seems to be about 0.2, where we start to really lose our analogs at these sites. So once you move a little bit down lower in elevation from our Craters of the Moon site is where you really hit this break point, and you lose analogs to the point where you have no analogs, or essentially what you could refer to as a novel climate. So a good example is Boise. Boise is projected to be a novel climate by mid-century. So what does that mean, though? To me, I think it means that, yes, more weeds, but that doesn't necessarily mean that there'll be native plants that will be adapted to those sites as well. And I think that's where a lot of research needs to be done. One of my hunches is that a lot of these plants that would fit these novel ecosystems are going to be found in the kind of the transition zone between the Mojave and the cold desert ecotone. But hopefully more information will come out soon on that. So quick summary here. The Climate Smart Restoration tool can be used to develop proactive strategies for both species and population selection. seed transfer guidance is available for all species, but the specific approach depends on availability of research. So if you don't have much research available in the species of interest, you should probably think that you should probably use a generalized seed transfer approach as opposed to looking for empirical. Across the board, local seed sources will become maladapted the next 20 to 30 years. I would recommend starting to think about mixing local sources with the projected future sources to maintain viability into the future and also increase genetic diversity in these sites. And again, warm, dry sites, these lower elevation sagebrush sites are expected to transition into novel climates by mid-century. And probably one of the more important points I'd like to make is this is a model, and obviously local knowledge is key to all this. This tool does not account for soils, past fire, and land usage, something that you need to rely on other tools like what Michelle described in her tool to think about some of these other aspects. Just like to thank numerous people in developing these tools and our funders. And lastly, just give you a list of the literature that supports these tools. Thank you.